The only objective for today is by the end of class, you need to be able to describe the life cycle of stars for both large mass and small mass stars because they are different. We're going to be talking about stars being born and stars dying today, so it's only right for me to mention to you that stars are not, in fact, living organisms, so they cannot live, die, be born, etc., but those terms make sense to our human minds, so we're going to apply them to stars, okay? So today we're going to talk about life cycles of stars from birth to death. We will start in the nebula. All stars begin here. Okay, so the life cycle of stars always begins here, no matter what size of star you are. What happens is you have a nebula, which is a cloud of gas and dust, and gravity starts to collapse that nebula. So the densest and darkest parts of the nebula start to collapse and condense into what we call a protostar. The protostar is going to continue to contract, and as it contracts, it's going to pull in gases and dust from the nebula around it into it until its core becomes hot enough and dense enough for nuclear fusion to take place. The process of that protostar pulling things in and condensing produces and releases a lot of heat. That heat is important because that's what's causing this baby star to heat up. Okay, so you have a protostar and it won't officially be qualified as a star until it can go through nuclear fusion, and in order to do that, it needs to get hot. Over many years, the heat of those protostars heats the gas and dust around them to the point that nuclear fusion can take place. Okay? Eventually, once this star is formed and nuclear fusion is happening in the center of the star, the gas and dust left over that didn't form the star will get blown away into outer space, and it will clear a path for us to be able to see the new star. Okay? The size of the star, so whether or not it's going to be a medium-sized star like our sun, larger stars would be made of more material. Okay, so depending on the size of the nebula, you might have multiple stars, you might have one really big star, depends, okay? And I do not know the answer to why some stars tend to form with more gas and some with less. I think it's probably just to do with the availability of gas near them when they start to form, okay? The star is going to be a main group star from the moment it starts fusing hydrogen into helium until all of its hydrogen runs out and it stops fusing hydrogen into helium. That whole time, which is the majority of the life of a star, it will be a main group star. When stars burn through their hydrogen and they use it all up and all they have left is helium, they can no longer stay in the main group. They must move on. Now, to our brains, it makes sense to think, well, larger stars have more helium, therefore they will exist as a main group star for longer. But in fact, the opposite is true because while large stars do have more hydrogen, they burn through their hydrogen way faster. It has to do with the size, creating pressure, causing the fusion to happen faster, and so they burn through their hydrogen really rapidly, and as a result, they have shorter lives overall, and they spend less of them as a main group star. So, we finished with the portion of the life cycle that is the same for most stars. Start as a nebula and a protostar, and then they become a main group star. Now, they might be different sizes of main group star, but that's where the sameness ends, and we move into things that are similar but not identical. And that's getting off of the main group into non-main group stars. Okay? Not all stars are going to go through every stage that we talk about today. I'll try to keep pointing out which ones do which. Okay? So we'll start with a red giant. When stars use up their hydrogen supply, then gravity is going to cause that core to contract and heat up. Basically, what happens is while fusion is happening, you have the outward force provided by the fusion on the star balancing the inward force of gravity. But when all of the hydrogen is used up and fusion is no longer happening, then that outward force stops and the star contracts. So you're saying, Mrs. Von Lau, I thought you said this is a giant star, but doesn't contracting mean it gets smaller? Initially, yes. Initially, it's going to contract down to the core. But what happens is when it heats up like that, the thermal energy from the center causes all the gas layers that are outside of it to heat up and expand. And when they expand, they spread out away from the core and cool down, which is why it goes from being a hot star, like a yellow star, to a cooler one, like a red star. Okay? Much larger in size, but cooler in temperature and producing less brightness. The star has become a red giant. Eventually, the interior of the red giant will become hot enough to resume nuclear fission. But at this point, there's no hydrogen left to react. What's reacting is that helium is becoming carbon. So our sun will someday become a red giant. And when it does, it will consume the inner 3 planets, most likely. Okay. Now, our star, the sun, will not become a larger red giant because it doesn't have enough mass. But for stars that do have enough mass, the process that we just looked at can actually repeat. What happens is when that helium core runs low, and it stops being able to fuse helium into carbon, it'll collapse again, and the star will become a red giant again, but it will be even bigger than it was last time because it will get hotter, cause the gases to expand even farther, and be a much larger star. Okay? And this time, in the nucleus, it will fuse carbon into other heavier elements. The largest of mass stars can continue to repeat the process that we just saw, and that is how we get supergiants. Okay, so a star that has enough mass can keep going through this process of using up all of the fusible material in the core, collapsing, heating up, fusing more material, and so on, and get bigger and bigger. Okay? Different elements are formed during fusion, all the way up to iron. In the most massive supergiants, they form iron in their cores. And then iron is a very stable element, which means it would take really incredibly high temperatures in order to fuse it. And we'll talk about what that looks like later. But when you have iron in your core, you have reached the largest supergiant form that you can take, and you must continue in some other direction. Now let's talk about the end of a star. So all stars start as nebula, then become protostars, then they are on their main sequence either as a large star or as a medium to small size star, and then they can exit the main sequence and become a giant, and for larger mass stars, eventually a supergiant. Okay? But this is where two paths diverge, because the end stage for medium to small mass stars is significantly different than the end stage for larger mass stars. Okay? Let's talk about white dwarfs, because this is the ending for a lower mass star. And for some reason, when I was typing this, I was having a really hard time, and I kept putting the word Earth in for sun, and I guess it slipped through once. So this right here where it says lower mass stars like the Earth, sorry, Earth's not a star. That was intended to say sun. Okay? Lower mass stars like the sun don't have enough mass to fuse elements beyond helium, which goes into carbon. So once we've fused all of the helium that we can into carbon, they don't have enough mass to go beyond that. So they can't become a larger red giant or even a red supergiant. They have to stop here. And what happens is when all of the helium in their cores is gone, they cast off the gases that are around the cores, and it leaves just a white hot sphere of carbon that's going to slowly cool over the next, millions of years. And that core is called a white dwarf. A planetary nebula forms when a star becomes a white dwarf. Now, the name for this is a little bit confusing because planets don't actually form here. The reason they're called planetary nebula is the name that the people who named them thought it was where planets were forming. They were in fact mistaken. What a planetary nebula actually is all of the leftover gases that couldn't be fused when the white dwarf casts off its outer atmosphere and sends all those gases flying. They become a planetary nebula. And that nebula can later on form new stars. So you can see why we would call this a life cycle, because the end of the star can actually be the beginning of new ones. Then in the center of the planetary nebula, the white dwarf will eventually cool, and as it becomes less and less luminous, it will fade to a black dwarf, or a brown dwarf, as some people call them. So now we have the full life cycle for a lower mass star, right? Nebula to protostar to red giant nebula to protostar to main group star, red giant, white dwarf with a planetary nebula around it. Eventually fades out into a brown or black dwarf. But the ending for larger mass stars is not the same. Okay? Stars with masses more than 10 times the sun do not become white dwarfs. Instead, they explode into what we call a supernova, which is an enormous explosion that destroys a star. What happens is, when iron forms in the core of the star, it's very stable, so it's not going to fuse into new elements. But without that internal fusion happening, when that fusion stops, those forces unbalance again, and there's no force outward on the star, so gravity takes over and collapses that star quickly under the force of gravity, and so much energy is released by that contraction that it just explodes. And in that explosion, all the elements of the periodic table are created because the temperatures and the energy of that explosion is massive. So, in fact, a lot of people think that an explosion similar to this is how the original matter of the universe was created and spread out into the universe. Okay. If you were a large mass star, okay, this would be one of the final stages of your life. The last stage in their life cycle is called a neutron star. The collapse of a supernova is so incredibly violent that it can actually force the electrons and protons in atoms to combine and form neutrons. And what it does is it basically collapses all the empty space in the atoms and packs all of that mass left over from the explosion into one space. This causes the formation of something called a neutron star, a dense core of neutrons that remains after a supernova. Now think about how big stars are, and obviously some matter is blown away during the explosion, but a lot of that matter still remains. So to collapse that much matter into 20 kilometers, that will tell you how incredibly densely packed a neutron star is. It is very dense at the core. For the absolute most massive of stars, a neutron star is not the final stage, okay? For the most massive stars, the forces that hold a neutron together are not enough for the mass that is collapsing down on them. That force is too great. And so gravity actually crushes that neutron star and turns it into a black hole. As we have discussed, a black hole is an object whose gravity is so great that no light can escape it. And that is the ending of the most massive stars. Okay. So that is the end of our notes. Your homework is the check for understanding that should be posted on Classroom by now.